Okay, before we apply the first law, we've got to learn a little bit more property information. We've got to understand a little bit more about different phases. We've got to understand a little more about how we look up internal energy, specific volume, pressure, temperature. How are they all related? They're all related through property information, okay? And so we're going to begin digging through some of that, and we're going to continue into that next week. This stuff isn't the first law. This stuff really is completely separate from the course in some ways, but yet we need to know all this stuff in order to apply any of it into first law, second law, all this stuff, okay? So the property information is a big chunk of knowledge that we need to have in order to do anything, but in and of itself, it's not a whole lot of thermodynamics. It's more like chemistry, I guess, or physics, okay? In and of itself, it's just learning about properties and phases and things like that. But we need to know it, so we got to cover it, and it's very important, very, very important. So the good news is, though, is we're mainly going to focus on two things you're very familiar with, air and water, okay? And the good news is air and water are a big part of many thermodynamic systems, okay? Yes, we will cover other things besides air and water, okay? Sometimes we'll cover refrigerants. Sometimes we'll cover things like other gases besides just air, okay? We might have more of like just pure oxygen or nitrogen or something like that. We might have some other substances here and there, okay? But most of what we do is going to be air and water. That's good, okay? Because I think we can relate to it. All right. So first thing we're going to do is we're going to talk about heating water. We're going to pretend like we're boiling some water, okay? And we're going to do it in the context here of a TV diagram, okay? By TV, I don't mean television. I mean temperature versus specific volume, okay? So we've got one axis here that has temperature and another axis here that has specific volume, okay? Now in this case, we're going to have the temperature be in degrees Celsius, and the specific volumes are going to be in meters cubed per kilogram, but it certainly doesn't have to be. Okay? So we're going to pretend we're boiling water. Now, when you go to the tap, to wherever you get water from, and let's say you're making some mac and cheese or whatever, you're probably going to get water, just taking a guess here, that's maybe around 20 degrees Celsius, maybe a little colder in the winter. I don't know. We'll just say it's 20 degrees Celsius, okay? Now, when you get water that's 20 degrees Celsius, I'm going to put a point right here for this. What's the specific volume going to be of that water? Well, remember, specific volume is 1 over the density. Does anybody remember what the density of water is if it's just, tap water? Yeah, 1,000. Basically, it's 1,000 kilograms per cubic meter. So then what's the specific volume? Yeah, well, I think we could do that math, right? What's 1 divided by 1,000? 1,000, yes. 0.001, right? So the specific volume would be roughly 0.001 meters cubed per kilogram. Okay? Roughly. Okay. Now, we take our pot of water, and we're going to start heating it. Before we start heating it, though, there's a term, a thermodynamic term for this kind of water, okay? We call it compressed liquid. So next time you're ordering at a restaurant, just say, I'd like a glass of compressed liquid water. They'll probably look at you like, what? Just give me a glass of compressed liquid water, please. Maybe you're with the family and, hey, Ma, could you go get me a glass of compressed liquid water? Thanks. I really appreciate it. Okay, because that's what it is. That's what you're drinking. Compressed liquid water. I hope it's nothing else. I think you're just drinking compressed liquid water. Okay. So then you put it on the stove and you're going to start heating it. Okay, you're going to start heating it. And obviously, when you start heating it, the temperature is going to go up and a little bit the specific volume is going to go up. You're not going to be able to notice much the specific volume going up, but it'll go up a little bit. Not much. What's that? Yes. Then we're going to heat this thing up to about 100 degrees Celsius. Here we go. Now, we're doing an assumption here, but it's a pretty valid assumption, and that is we're doing an assumption that says that we are in a, regular standard atmospheric pressure of about 100 kilopascals, roughly 101 kilopascals. 1 atmospheric pressure, regular pressure, air pressure around here. Okay, so we do that, and we heat your water to about 100 degrees Celsius, about 212 Fahrenheit, right? We're heating it, and we notice the water just starts to boil. I mean, just barely. Just you're looking, and I see boiling. Okay? I see. Then what you have is another state we like to call saturated liquid. Saturated liquid. That's water that has just started boiling. It's all water still. It's still water, but it's just on the brink of boiling. And it's just started boiling. Okay? And we know that at standard atmospheric pressure, that would happen at about 100 degrees Celsius. Okay. Then we start to boil. If you put a thermometer in boiling water, as you continue to boil it off, it never goes up in temperature. It stays a constant temperature through the boiling process. So then it's going to be flat like this. Okay? And what's going to happen is as you boil it, you're going to boil off all the water. If you're looking at the pot, it's all going to boil off. As you start watching it, the water level is going to drop and drop and drop and drop and drop until you boiled it all off, right? And what you have at that instant, when you boiled it all off, and it's all vapor, okay, we call that saturated vapor, okay? So now we've got this term here, saturated vapor. You boiled it all off. It's all vapor now, sat vapor. Okay, now, this next part's a little harder to imagine because if you're in your kitchen and you boiled off all your water, it's gone. You can't really heat it anymore because it's just in the kitchen. You might see some, evaporation back above and, cabinets or something or wherever, but you might see condensation, above in the cabinets and things like that. You might look in the ceiling, I see some condensation in my ceiling, but you really can't heat it any further. Let's instead imagine that you had a very, very large pot, and the pot, wasn't so sealed or whatever but that you could mainly contain that saturated vapor because we want to keep heating it. Let's say we can keep heating that saturated vapor. What if you keep heating it past the saturated vapor stage? What happens is that the temperature starts going back up again. Okay, the temperature starts going back up like this. Okay, starts going back up again. And when you start heating it some more, you get to a state called superheated vapor. No, it's kind of curved. Both of them really are curved. The only straight line is the one in the middle. But, the curvature on the first part's pretty minor. Okay? Now, recognize, again, all of this was the assumption that I had a constant pressure process. The pressure for the whole process was 1 atmosphere. Okay? But in thermodynamic applications, it's not always 1 atmosphere. It's not always regular standard atmospheric pressure. So I'm going to add something else to this drawing that's very important. I'm going to add what in thermodynamics we like to call the dome. Okay? So let me draw for you the dome, and you do your best to draw it as best you can. Something like that. Draw that as best you can. Make sure that the saturated liquid point meets the dome on the left side, and make sure the saturated vapor point meets the dome on the right side. Okay. But that drawing, I mean, if I went and showed this drawing to a lot of engineers who, you know, have been out of school for 20, 30 years, they'd go, oh, that's from thermo. That's how recognizable it is. They'd be like, oh, yeah, that's thermodynamics. I know what that is. That's the dome. It's famous. It's the dome. Yeah. Yes, it does. The compressed liquid line has to be to the left of that blue line. Yes. The compressed liquid has to be, this whole part has to be to the left of the dome there. Yeah. Yeah, it has to be. It does meet the blue line at the saturated liquid. Because basically what the dome says is this. If you're on the left side of the dome, you're compressed liquid. So over here, it's all compressed liquid. In the middle, it's what we like to call saturated liquid vapor mix. And on the right side of the dome, the whole region to the right side of the dome, it's superheated. The dome separates out all 3 phases, all 3 parts. Compressed liquid, saturated vapor. In the middle, inside the dome, is always your mix between liquid and vapor. It's both. One more thing I want to draw for you. What if the pressure were greater? What if the pressure were greater? Well, we would have another line of constant pressure. A greater pressure might look something like this. Oops. A greater pressure might look something like this. Okay? This would be a pressure greater than 1 atmosphere. I mean, I don't know exactly how much greater, because I just drew it arbitrarily, right? But what you see here is that if you have a greater pressure, it moves the line up, but it looks like the same shape, basically, the line, but it moves it up, meaning that your point for saturated liquid, your boiling point, the boiling point of water is higher when you have greater pressure. The boiling point of water is higher under greater pressure. The boiling point of water is lower under less pressure, meaning that if you boil water at high atmosphere, if you go up into the mountains or something like that, you try to boil water, it will boil at under 100 degrees Celsius. It may boil at only 90 degrees Celsius if you're high enough. You know? It'll boil because it's less pressure up high elevations. But in a lot of thermodynamic applications, we have greater pressure. So if it's greater pressure, then it actually boils at a greater temperature. By the way, that's why a pressure cooker works so well. Not that people don't use pressure cookers too often anymore. Yeah, you still like them? Yeah, a few people do. People have seen them. But a pressure cooker works so well in cooking fast because it keeps the water from boiling at such a low temperature. It can boil at a higher temperature, therefore it's hotter water. Okay? So, it cook faster. And you might be asking yourself, well, what about the top? What goes on above? Okay? What you have at the top is what we call the critical temperature and pressure. Okay? Here is the critical temperature. It also exists there as the pressure. Critical temperature and pressure. It's very hot and very high pressure, but it can be exceeded in thermodynamic applications. If you have a pressure greater than the critical pressure, okay, if you're up way high like that, the line between the liquid phase and the vapor phase becomes more blurry. Okay, it becomes unsure. Okay, if you get real high, it gets real blurry where you're at. It's not so clear. Inside the dome, it's real clear. We have tons of evidence, and we know exactly where you're at if you're inside the dome. But when you get above the dome, you get above that critical pressure, and it's not clear anymore whether you're in the liquid or the vapor phase. Okay, it gets a little bit hazier. Now, generally, if you're at the critical pressure but you're low temperature, you're probably in the liquid phase, and you're high temperature, you're probably in the vapor phase. But the region where it's in the middle, it's hard to define. It's not so clear. Okay, when you get these really high pressures. Okay, so we call that the critical temperature. Okay? Critical pressure, sometimes also referred to as critical pressure.
But is that what the supercritical fluids are?
Yeah. If it's supercritical, then it's beyond that. Yep. Okay. Most of the time, we'll be in the dome or with the dome. We won't go above too much. Okay, it does happen, but it's pretty high, and it's pretty much out of the range of a lot of applications. But it does happen. Okay, and but this is a very important relationship. We're going to use this kind of graph, a TV diagram. Sometimes it might be a PV diagram instead, pressure versus specific volume. I will tell you that the pressure versus specific volume dome looks very similar. Okay, it might be a PV diagram. Okay, and then we're going to use some other diagrams, but it's going to be helpful for us to use these diagrams so we understand where we're at in the dome, because that's really important. Okay? All right, what I want to do now for the last few minutes, if you have a book or anything that has the property information, I want to go back there and just walk through some stuff with you. If you don't have the property tables, I'm going to bring them up on the screen here. Okay? I'm going to bring them up. But it'd be easier for you to read in your book. Let me tell you this. When we're here on Tuesday, I want everybody to either bring the book or bring a printout of the property tables. Okay? I sent everybody a PDF of all the property tables. Feel free to print it out. You don't have to lug the entire book if you don't want to. I don't care. Okay? So that's fine. As long as you can read it. Can you read it?
I can really mark it.
Okay. If you're comfortable with that, I'm fine. Okay? As long as you can read it, it's good. Okay? But bring a book, bring the tables, bring something, because we're going to spend a lot of time on Tuesday going through some more of this stuff. Okay? We're just going to start today. Okay? So what I'm going to do is I'm going to bring up the property tables here. Let's see here. Okay. What you'll notice if you bring up the property tables, the first page, it's somewhere around 905 in the textbook. It depends on which version you have of the book, but somewhere around that. You'll notice that you have Appendix 1. It says Property Tables and Charts for SI Units. Okay? Then if you scroll about another 50 pages, if you go another 50 pages in your book, you will get to Appendix 2. Where is it? Here it is. Appendix 2, Property Tables and Charts. This one's for English units. So the English units, again, would be like BTUs, pound mass, Rankine, things like that. Okay? Nearly every single table that you have in Appendix 1 is the same thing in Appendix 2. They're both the same information. They're just one of them has the metric units and one has the English units. Okay? So you got them all in your book, in your tabular data. Okay? Make sure you know that. Sometimes you have to go to this Appendix 2. By the way, when they have tables in Appendix 2, it'll say Table A to E. It'll always put the E there just to let you know, oh, by the way, that's English units. Okay, we're going to go back to the first appendix, though. All the way back to the beginning, proper tables and charts. There's lots of different things going on here. Look at this. You've got, what, 34 different tables. Okay? 34 different tables. But I will tell you this, you will use a lot of these tables. You certainly won't use all 34. But you will use quite a few of these. But I will tell you that tables A4, A5, A6, and A7 are going to be by far the most common. Okay, particularly 4, 5, and 6. But 4, 5, 6, and 7 are going to be the ones we use a ton. Okay? Going to get used to those. All right? Going to use those a lot. Okay, so let's go to table A4. Okay. Saturated water temperature table. Okay? Then I also want you to notice, if you turn the page or scroll down, whatever, that you have table A5, saturated water pressure table. Okay? Basically, these two tables have the exact same information. They're the same thing. Okay? But one of them is listed by temperatures. So, for instance, notice the temperature, the first column here on the saturated water temperature table, table A4. Look, all the temperatures are nice numbers like 20, 25, 30, 35, 40, 45, 50, 100, 105, 110, 120. See, it's all listed by temperature. You can go all the way to the highest temperature they have is 373.95 Celsius. Okay? It's all listed by temperature. And the next part, it's all listed by pressure. All listed by pressure. It's the same information. Okay? Because when you're in the saturated part, okay, when you're saturated, whether you're saturated water with saturated water, the temperature and pressure are dependent, which means this. If you tell me, oh, I have a saturated water, and you tell me what the temperature is, I automatically know what the pressure is. If you have saturated water and you tell me what the pressure is, I automatically know what the temperature is. For example, take a look at the temperature of, let's go here to 180 degrees Celsius. If you look up on table A4, saturated water temperature table for 180 degrees Celsius, you get a pressure of 1,002.8 kilopascals. Basically, it's 1,000 kilopascals, okay? Remember, atmospheric pressure is about 100 kilopascals. Yeah, 10 atmospheres, yeah. 10 times atmospheric pressure. So remember, 180 degrees Celsius corresponds to about 1,000 kilopascals. Now, go to the pressure table. Go to the next page, pressure table, and I want you to find 1,000 kilopascals on the pressure table. 1,000 kilopascals on the pressure table corresponds to a saturation temperature of 180 degrees, 179.88. Okay? So again, the information contained in the temperature table is really identical to the information contained in the pressure table. You would use the temperature table if they gave you a temperature. You would use the pressure table if they gave you a pressure. That's it. Okay? But they're dependent on each other. Once you have the pressure, then you have the temperature. That is only true, by the way, if you are saturated liquid vapor mix. If you are saturated liquid vapor mix, if you're inside the dome, then you are on this chart, saturated water. Saturated water on this chart corresponds to inside the dome, saturated liquid vapor mix. That's what that means, okay? So, doesn't really matter which one. I can stay here on this pressure table. 1,000 kilopascals gives me a saturation temperature of 179.88, which means this. If I were to have a high pressure and have 10 times atmospheric pressure, I'd boil water at 180 degrees. So it'd take me 180 degrees Celsius to boil water. That's quite a bit higher than regular, right? That's because I have higher pressure, 10 times higher pressure. Okay? Now notice this. Let's walk through this. The specific volume is the next two columns on the chart. This first one says saturated liquid. The specific volume of saturated liquid is 0.001127. The specific volume of saturated vapor is 0.19436. If you think about it, that's a massive difference between those two numbers. That's a big, big difference because you have to move that decimal place 2 times. So it's over 100 times bigger volume. Saturated vapor contains a lot more volume than saturated liquid. Water, once you boil it, spreads out. That kind of makes sense, right? It has a lot more volume. Okay? And so what we have here is a table that gives us the specific volume of saturated liquid and the specific volume of saturated vapor. What else do we have? Internal energy is the next 3 columns. We have the internal energy of saturated liquid at 1,000 kPa as 761.39. And we have the internal energy of saturated vapor at 1,000 kPa as 2582.8. Now you may ask yourself, what's this middle number? What's the evap? The evap is just the difference between saturated vapor and saturated liquid. It really does not have to be in the table. It's literally just the difference between sat vapor and sat liquid. If you were to take sat vapor, 2582.8, and subtract 761.39, you would get 1821.4. It's just the difference between the two. You will find out very soon how handy that is, though, to have that evap term. Okay, I will tell you that evap term is very handy, but there's not really any new information. It's just the difference between the two. Okay? Internal energy. Notice it's, look at the little U's there. U, U, U. Okay? And by the way, I will be using this designation. UF means sat liquid and UG means sat vapor. I always remember it by F stands for fluid and G stands for gas. That's how I remember it in my mind. UF is going to be the sat liquid when it's all liquid, internal energy when it's all liquid. UG is going to be internal energy when it's all gas vapor. The next 3 columns are something that you haven't seen before, called enthalpy. It's denoted by the letter H, enthalpy. Okay? And our H's are going to be very important. We haven't introduced enthalpy yet. I actually kind of have introduced enthalpy to you, but you didn't know it. But you're going to see it very soon amount of time. We will show you enthalpy. Okay? Sat liquid, sat vapor, and then the difference between the two is the evap again. That's just the difference between the two. There's nothing really special about it. Finally, the last 3 columns are something called entropy. It's denoted by the letter S. Entropy has to do with the second law of thermodynamics, and we haven't got there, and we won't get there for a while. I used to say it'd be spring break, but our spring break's kind of late, so I think we'll be at enthalpy before spring break. You know, spring break's like the last week of March. Okay, so we'll probably be starting to talk about entropy. We'll be talking about entropy before then. Okay, entropy has to do with the second law of thermodynamics, so we won't touch it until we get to the second law, and that'll be a little while. Okay, that's kind of how you read your chart. Now that's saturated water, but that's not the only charts. Okay, they're probably the most critical. I mean, they're some of the most critical charts. But let me show you. If you continue on, you also got superheated water. Now, superheated water is different than saturated water. If I have superheated water and I tell you what the temperature is, I don't automatically know what the pressure is. With superheated water, temperature and pressure are independent. So I have to get both. So in this case, I've got a bunch of little tables here. I've got a table for 0.01 megapascals, 0.05 megapascals. I got a table right here for 0.1 megapascals. By the way, 0.1 megapascals is 100 kilopascals, is pretty much what our atmospheric pressure is. Notice the boiling point is 99.61, 100 degrees Celsius basically, right? Okay? That's what that is. That's superheated. But look, we keep going. Increase the pressure. 0.2, 0.3, 0.4, 0.8. Keep going. 1, 2, 3. Keep going. Lots of them. 4, 5, 7, 12 and a half. Keep going. All the way up to 60 megapascals of pressure. 600 times atmospheric pressure. That's a lot of pressure. We have a table for it. Okay? We have a table for it. So this is all superheated water, okay? So when we talk about superheated again, we're talking about the right side of the dome, okay? Last but not least, compressed liquid. We don't have as many compressed liquid tables because frankly we don't deal with compressed liquid that much in thermodynamics. We do sometimes. And sometimes we actually have some short calculations we can do to simplify it. But they do give you a few compressed liquid. Next time, everybody, make sure you have the tables because we're going to dig in even more.